So, long story short, conduction mode refers to how current is varying in the energy storage element in a switch mode power supply. In a basic converter, you can have a continuously variable current, or continuous conduction mode, which is a nice triangle waveform, or you can have a current that varies and then stops varying. So, discontinuous conduction mode. Now, these are some generic waveforms, but what more is happening in the converters? Well, if you're curious, then keep watching. Now, although the conduction mode analysis and principles apply to any switching converter, today I will be focusing on a basic boost converter. So, let's start off by looking at the main states of the switching converter based on what the switching element is doing. Now, a basic switch mode converter analysis assumes two states or phases. One in which the switching transistor is on, when energy is being stored in the inductor, and the second phase in which the switching transistor is off, when the energy is taken from the inductor and delivered to the load. In our first phase, we have a rising current profile, and in the second phase, we have a falling current profile. And overall, the current is continuously varying. Once one phase ends, the other one begins. And this is what continuous conduction looks like. Now, depending on the component choice and load, we can, however, get a third phase appearing. So, other than the inductor charging and discharging, in certain cases, you can end up with a state in which the inductor runs out of energy, so no more current passes. At this point, none of the switches in the converter are conducting any current. And this leads us to discontinuous conduction mode. This is characterized by a period in which the inductor current is stagnant at zero. Now, at this point, it's important to mention that this analysis holds true with asynchronous converters, ones in which one of the switches is passive. So the diode will only turn on when the conditions are met to forward bias it. The diode does not care what the converter logic is doing behind the scenes. In a synchronous converter, however, where we replace the passive diode with an active switch, we can have an interesting phenomenon appearing. So, of course, we can have our normal continuous conduction mode, just like with the asynchronous converter, where current runs as before, so with the two phases. But if we forcefully keep the second switch on, even when the inductor runs out of current, we can prevent discontinuous conduction mode by reversing the inductor current. Basically, the converter will start taking energy from the output and giving it to the input. It will start working backwards. This is quite inefficient, but it is the price you will sometimes be willing to pay to prevent discontinuous conduction mode. So, with this method, you will always have a continuous current running through the inductor, even if sometimes it's going forward, sometimes it's going backward. So now that we have a basic understanding on what the difference is between the two conduction modes, it's time to look at some of the performance changes. If you had a choice, why would you go with one mode over another? One of the interesting things to discuss is how the output voltage is related to the duty cycle. So with continuous conduction mode, for most converters, you have some form of basic equation with the input and output voltage from which a duty cycle can be determined. This can of course be complicated a bit when you factor in various losses, but the point is that while the converter is kept in continuous conduction mode, the duty cycle is mainly dependent on the input and output voltage. Discontinuous conduction mode is a completely different story. Even without considering the various losses, the duty cycle is a complex equation that is impacted not just by the input and output voltage, but also the inductor value, output load, and the switching period. This can give some headaches. The loop response is different under discontinuous conduction mode compared to continuous conduction mode, but at least it can be made to react faster. Also, on the positive side, as long as the duty cycle range is fixed to some interval, in most real power supplies you can't get any value, there usually is a minimum and maximum limit. For the sake of example, let's say it's 10% and 90%. With this limitation in mind, under continuous conduction mode, the output voltage will be limited to a maximum of 10 times the input voltage. In discontinuous conduction mode, this limitation no longer exists. By playing around with the various values, you can potentially get any output voltage range, even though you have a limited duty cycle. This of course will not be all that efficient, but at least it's possible. And sometimes you might actually need this. Speaking of efficiency, one of the things to observe, if we compare a converter built for a fixed load, that is once designed to work in continuous conduction mode and once in discontinuous conduction mode, the exact current values that pass through the converter will be different, and so will some of the components. First off, the way in which you force discontinuous conduction mode is to use small inductor values. The smaller the inductor is, the faster the current will change through it. In other words, the current will vary quicker. If we plot out the typical inductor current for the two modes of conduction, we will observe that the RMS and peak current for discontinuous conduction mode will be larger. Now, from an efficiency point of view, this is not really a problem, since a smaller inductor in the same package will usually have a smaller on resistance, so this particular topic should not affect efficiency. Next, if we look at the diode current, we see the same average current in both cases, the output load is the same, so the efficiency should not be impacted all that much, but we still need to take care that the peak diode current under discontinuous conduction mode can actually be handled. So sometimes you may need higher current rated diodes to allow for discontinuous conduction mode. Finally, the switching element, we have a higher peak and RMS current, so if we use the same transistor for both modes, the conduction losses will be higher in discontinuous conduction mode. Now, there is one phenomenon that will help with efficiency though, and that is zero current switching. So with continuous conduction mode, both the diode and the switch current jump from 0 to some value, and then back down to 0, making the transitions quite inefficient. However, for discontinuous conduction mode, one of the transitions goes from a certain value to 0, while the other begins at 0. So at least the switching losses can still be made smaller in discontinuous conduction mode than they are in continuous conduction mode. Now, for the converter as a whole, it depends. Some converters can be built to work more efficiently during discontinuous conduction mode, while others will be more efficient in continuous conduction mode. So what other considerations are there regarding the choice between the two operating modes? In general, having a larger current variation and higher current peaks, as is characteristic for discontinuous conduction mode, will cause greater electromagnetic interference problems. The larger the AC component of the waveforms, the more noise they will generate. But other than the current, it's important to also observe the voltage in such a converter, since this usually has a very specific shape. To highlight this, I will be performing some LT-SPICE simulations on a modified version of one of the default schematics present in the library. So the test fixture for the LTC1871. So as the circuit is, if we run it, and we look at the inductor current and just zoom into the area in which it's stable, we can see the typical current waveform for continuous conduction mode. A very nice triangle waveform. And if we also look at the switching node voltage, and we just put it into another plane, we can again see the typical waveform. So an almost square wave. So the first thing that we can highlight is the way in which you would force this converter into discontinuous conduction mode. So right now the standard inductor is 1 microhenry, but if we use a much smaller inductor, say 200 nanohenries, and we look at how the circuit works, so first of all, we check out the output voltage in the two cases, it's more or less the same, 5.0 something, so the circuit still works. However, if we now check out the inductor current in our second circuit, we can already see a clear difference. So the current rises, falls, and then stays flat for some amount of time before the next switching cycle. And if we compare this to our initial current, so we can already see that the peak current is completely different, it's much higher with our discontinuous conduction mode. And if we check the RMS currents, so for the continuous conduction mode circuit it's about 8.9 amperes, for our discontinuous conduction mode it's 11.07. Now the other thing that I wanted to highlight is the voltage in the switching node. So we still have our squarish shape, but that is followed by an oscillation. So we have an almost perfect sine wave appearing. And if we also plot out the inductor current at the same time, we can observe that this oscillation is occurring when the inductor current is at 0. So this sort of oscillation in the switching node will be visible in any converter running in discontinuous conduction mode, and it is impacted by the inductor's value and the various capacitances in the circuit. Point is that when you're concerned with electromagnetic interference, having a nice oscillation appearing in your circuit is not something that you want. So why is it here? Well, in a theoretical analysis with ideal diodes, the switching node transitions between 0 when the switching on and the output voltage when the switch is open. So the ideal diode has no voltage drop on it, so the switching node is at the same potential as the output. And then once the inductor current runs out, the diode instantly blocks, and the voltage in the switching node will be equal to the voltage on the other end of the inductor. In the case of the boost converter, this is the input voltage. After that, the next switching cycle begins, so the voltage will again drop to 0 when the switch is on. Now, in reality, there are a few things missing from this analysis. First, there is quite a bit of capacitance in the switching node. The inductor has some parallel capacitance, so does the switch and the diode. And of course, the traces should not be forgotten. So even if there is no more current in the inductor, all of these capacitors are still charged up to a certain voltage. So when the diode suddenly stops conducting, these stray capacitances, together with the inductor, form an oscillator. And all of the energy left behind starts to oscillate until it either gets dissipated over the various resistances or until the next switching cycle begins. So even though you don't want to see this sort of effect, seeing an oscillation in the switching node in converters running in discontinuous conduction mode is perfectly normal. This is typical for any converter. So you'll see this oscillation in buck or boost or any other converter. So even if you don't have the possibility to directly measure the inductor's current probes are quite expensive, seeing this sort of oscillation is a telltale sign of the particular conduction mode. In most practical cases, a switch mode power supply will end up operating in both continuous conduction mode and discontinuous conduction mode, the latter being under low load conditions. With synchronous converters, you can force continuous conduction at the expense of extra loss, but if that really is necessary, is usually use case dependent. Anyway, you should make sure that the converter is stable in both cases, even if discontinuous conduction mode is not the normal use case. And with that said, hope you enjoyed this video, and if so, there are more similar videos on my channel that you might want to check out. And if you want to stay up to date with my latest releases, you can also consider subscribing. So, see you next time. Bye bye.